Thank you for the introduction. So yeah, unfortunately, Ishan cannot be here for some visa restriction. So I will present his master's thesis work. So it's one of his work during his master's thesis. And it's about Glint surface. So you can see some video that was took by Ishan. And you can see that, we want to render this kind of surface that exhibit a rich and glossy appearance due to some mesoscale structure like scratches, bump, and so on. And when you move around, then this appearance can change or when the lighting changes. In particular, when you have like a surface with a glint appearance, when you change the distance of the viewer, then it can change quite dramatically as well. So we want to have a rendering techniques that can, when you are close to the surface, to see the individual glint, but when you are far away, you want to see the aggregation of the appearance of all the glint. And this large collection actually is kind of challenging for do the integration, because if you just are far away and look at 1 pixel integration over the glint surface, then for particular lighting direction, basically there might be only a few glints that will contribute to the final radiance that you get from you, the viewer. And this is for one direction for the light. So imagine that you have to integrate, then it's more complicated integrating the incoming lighting. So the objective of this work is we have 3 objectives. The first one is to accurately model the multi-scale appearance of this kind of surfaces. Especially, we want to have to control the glint distribution using a normal map. Secondly, we want that the memory requirement for our techniques is not too high, because we might have some scene with multiple objects with some different glint distribution. And we also want optionally to support spatially varying roughness. And finally, at not least, we want to perform analytical integration of the incoming lighting and the glint distribution in order to avoid some noise. So like all the results that I will show you and the result section will be only 1 SPP, 1 sample per pixel, because we do analytical integration. So I will present some related work. So it's just like a very short version of the related work. If you want more discussion about this, just look at the paper. So first, let me just talk very quickly about the microfacet model that we use, or that is usually used in the glint rendering. I will not describe this function because I think we have seen this function multiple times. The most important part here is the D, that is the distribution of facet. And its model that is also called the normal distribution function, or NDF. And this models this kind of slope that you can see at the bottom of the screen here. And this NDF usually for some, in rendering, you are usually used to parameters with some kind of single parameter or 2 parameters, like alpha. And depending on this alpha parameter, you can have very smooth appearance or very rough appearance if the alpha is quite large. So, but even if you have this parametric model, here, like I show you 3 surfaces with the same base material, but different NDF, and you can see that, it might be difficult to model with this single parameter, this different appearance, basically, for this different surface. So there was some work that was focusing on this, basically, for this particular NDF formulation. So there was this one category of work that we call it implicit glint representation. So there is a bunch of work on this. And basically, it's another way of representing the surface as a statistical distribution. These techniques are very fast and very compact. For example, the work in the middle by Chairman is real time. And you can also have some work on this space that is dedicated to some special glint distribution. So the Raymond, so the one that is the most on the right, is for scratches. But usually this works it's kind of as it's a statistical distribution, it's usually limited to some of the distribution. You cannot express any distribution that you want. And so there is another category of work that is explicit glint rendering. And in this case, usually the artists or the techniques like take a normal map, and then these techniques build a hierarchical data structure or any representation. But then in rendering, you can just build the NDF very efficiently, like the PNDF or the NDF of the glint. So we can get the surface. So usually these techniques are very precise and can handle any arbitrary normal distribution function because you just have to provide a normal map for that. However, like not much of these techniques can support analytical integration. There is one exception that is work by Gamboa and colleagues, which combine the histogram-based NDF and spherical harmonics to allow analytical integration. And he in this work is using spherical harmonics because you have the nice property in spherical harmonics that if you express your incoming lighting in spherical harmonics, and also like the BSDF that represents your glint distribution in spherical harmonics, then for computing the integral of the products, it's just the dot product of the coefficient of the spherical harmonics. So it's just a dot product if you have this coefficient. And so if you can do that, then you can just render some images with one sample per pixel and integrate the light from, for example, environmental light. So we build, the work that I will present today is built on these techniques here. So now let's talk about the work. So basically, let's formalize the NDF distribution. So NDF distribution, first we want to avoid noise due to Monte Carlo rendering or not performing integration of the pixel footprint with Monte Carlo. So usually how it works, like we project the footprint on the surface, then the footprint is projected on the normal map, and then we can build the PNDF. So it's like footprint NDF by just counting or taking into account all the normal map distribution inside the footprint. And you see that, so you have the sum that is the normal distribution, and you have this kernel G that is just the roughness. You had a small roughness at each glint to get some kind of, you can have more appearance on this. So it's kind of a complex function. Here you have a 3D representation of this function. So to simplify it, Gamboa et al. What is done is like they do a discretization of this distribution. Basically, they take the normal orientation, they discretize them and put in the histogram. So you have now a histogram that represents the normal orientation. And then you still have the roughness for each of the orientation of your histogram being, then you will have a roughness parameter, so the intrinsic roughness kernel here. So our first contribution in this work was to look at what this histogram representation looks like for normal map. So in his original work, Gamboa and colleagues was using a regular binning strategy, meaning that the theta angle is discretized uniformly. But this can be not great for some kind of normal map because some of the, maybe some normal distribution are more common. So what we done here in our work was to just use adaptive binning. So how we do it is like we take all the normal distribution from the normal map, we run the k-means, we run the k-mean only on the theta, that is elevation, because we found that the rotation, so azimuthal, doesn't change much if we do that. And we can then build our histogram adaptively. And you can see that the histogram now, this is like the number of normal that arrive to each bin. We can see that we have a much more efficient representation. So how it looks like, this kind of adaptive histogram is like, you can see that there is some major change in terms of the appearance in some region, because we have now a better representation of the idea. And the reference is on the right here. Okay, so the cool thing about this adaptive histogram is that you can use it with Gamboa techniques. Is like Gamboa and our techniques support this kind of adaptive histogram. So you can still use the old techniques, but we didn't stop here. Basically, what we look at is also like how this histogram are built. So Gamboa and et al., what they do is like they was using some area table to build this histogram. I will not enter to the details, but the important things that you have to know is like you have, for each bin, you have this big texture, you query 4 times, you do some arithmetic on this, and you are able to compute the count for each bin, and it gives you the histogram at the end. It's quite simple. The main issue is like if you have a histogram resolution given here with a texture size that is 2K by 2K, it takes like almost 5 gigabytes. So like it might be difficult to have multiple objects with these techniques. So we tried during this project, we tried multiple stuff. Here we show you the solution, but just to tell you, we tried some kind of a better representation of the SAT, compression of the SAT. We tried indirection, differentiation indirection, and so on and so on. At the end, we found that the no-MIPS architecture that I will just describe here works the best. So basically, this architecture is based on some regular architecture, fixture vectors that is represented as a neural texture pyramid. So you can think about neural representation of the feature vector, but you do MIP mapping on this. So for a given footprint, basically you will find the 2 level, do trinomial interpolation, and then to get the latent vector that you can then pass to the MLP and decode the histogram. So at the end of this process, basically it will predict for each of the bin which is the count or which is the density of the normal that you get. And with this architecture, what you can do is like you can just reduce the texture resolution, because then the neural network will do the interpolation and also use half precision. And if you do that, then you have 50 MB. So it's more manageable for sure. However, if you just use that, it's working, and I will show you the result that it's working. But the main problem is like the number of output of your network is quite high, so you need a feature map. So the part of the neural texture pyramid is quite high, so it's difficult to train. It's working, but we can do better. And what we have done finally for our techniques was to do this partial histogram prediction. So we was just decomposing the histogram into a subset based on the elevation here. And then you predict for each, for example, row of your histogram, you predict the number of bin or the density. Then you kind of normalize the bin, and you are able to get the histogram back. So this architecture, you can see that there is multiple neural networks, there is multiple features. The memory usage goes up a bit, because now we maybe have less feature per neural network. And the neural network is much shorter. So it's good because then the neural network is very small, so it's fit to GPU memory, it's much faster. Even if you have n theta plus 1 evaluation of the neural network, then it's faster than the techniques that I presented just in the slide before. So what this looks like, so basically this is a reference. This is a baseline, so the baseline technique that was using only one neural network. You see that it's working, but you have some error in some cases. And this is when you do prediction of the partial histogram. It's much better, it works better. So now we have our histogram, our adaptive neural histogram. So we are happy about it, so let's render this histogram. So basically, you have this histogram that can usually expressed in the local frame. Your lighting is in the global frame. So what you have to do is to perform some kind of rotation of the circular harmonics coefficient in order to be in the same frame, so that you can do the dot product at the end. So it can be costly to do this rotation. So what Gamboa and colleagues have done was to do some kind of pre-computation. So you take all the possible direction of a discretized sphere, you compute some circular harmonics coefficient representation for all of this direction, and then at runtime, for a given bin direction, you just do binary interpolation to get the SH coefficient for this particular direction. Memory usage, I mean, it takes some space, order 60, you will see, I mean, the order we use usually for spatial harmonics, we use very high order here. The problem is like, this is a parameterization for this memory cost is only for one roughness. If you want to have multiple roughness, then you have to create this linear interpolation, and it would be much costly to do. So what we have used here in our work was to do zonal harmonics. So basically, zonal harmonics is a spatial harmonics function that's just model circular symmetric function, which is our case for our spherical Gaussian. That is the kernel, the G sigma S that we use here. And the cool thing about zonal harmonics is that you can perform fast rotation with this formula. So I will not go to details about this formula, but just let you know that this FL0 is a function that you just project. And then the YLM is this basis function that you have to evaluate on the rotation axis, or where you have to do the rotation. These two have to be computed. So what you can do is you can pre-computing them, the two. So for the first one, you just do like the classical projection of the SH. But for the second one, we have a special way to tabulate it. So it's quite fast. And actually, it's faster than the binary interpolation because it's reduced memory traffic and other things like this. So usually, even if you have to do this computation, it's faster. And it's more precise. So basically, the good thing is like when you do binary interpolation, you will do some error for sure. So when you do now fast rotation with zonal harmonics, with our tabulation, then the error go down significantly. And more importantly, the memory usage goes down like a lot. Actually, it's few megabytes, it's few bytes now. And what is good about that is that now you can just generate a bunch of spherical harmonics for different roughness. You just tabulated everything. Now you do a binary interpolation. Just an interpolation for the harmonics coefficient for the F0L. And then you can get this kind of nice thing about like you can edit the roughness of the surface on real time. You don't need to compute anything else, just do interpolation here. That was not possible with the techniques before. So let me talk about some results here. So the first result that you will see if you open the paper is this scene, that is our teaser scene. We have 4 objects. So, for example, Gambaro and colleagues, it takes like 6 seconds to render here, but it takes 20 gigabytes to render, to be rendered. So, hopefully, we have a 4090, so like it was enough memory to render that. But it might be difficult for other GPUs. In our case, basically, you can see down that you have timing for our technique. So the rendering time goes slightly lower, and actually now most of the computation is on the spherical harmonics dot product and so on. And the memory-wise, we go down significantly for 4 material. And in bonus, you can get this surface varying roughness. So, like if your kettle is a bit dirty, then you can make the appearance. Okay. So here, this is a kettle thing. So I will show you some video. Oh, it doesn't work because the decoder crashes. Okay, so I will just, I will not. Interesting. Too much compute. I will just reconnect. I will not show the video if it just crashes. You can find the video on the website. I will show you a link that you can just look at it. We have the project website, and then you can look at it. HDMI. Wait, it's good. Up. And so I will just. So it's quite fast. You will see in the video it's order 60. It's around 3 seconds to 1 second, basically. And you will see some video that we have zooming and like you have temporal coherency and so on. So in conclusion, we have techniques that we apply adaptive discretization that improve quality, the neural histogram reduce memory, and then on the fly rotation, basically improve quality, reduce memory, and then we can do surface varying roughness. So there is some limitation of the work, as there is not much time. I will just talk about just one of them. Is like we still use circular harmonics because was what we wanted to use here. But as I said, like most of the compute and the memory now of our techniques is based on these circular harmonics. So we might want to change it to other basis function. Thank you for your attention. As I said, if you go to this website, you will see the video code and everything like that. Thank you.